Hello and welcome back. Today we're going to learn about circular motion. There's actually going to be 2 lessons about circular motion. This is the first. In this lecture, we will learn about uniform circular motion, which is the motion of an object moving in a circle that's not speeding up or slowing down. So going at a constant speed, but in a circle. And then a little bit later, we'll learn about how to deal with situations in which you have objects that are speeding up or slowing down while also moving in a circle. So to get started, let's first consider a ball moving on a wheel. So this is a roulette wheel like you might find at a casino. The ball goes around in a circle, right? It's stuck in that spot. The whole wheel is turning. It's going to move along a circular path. We can say that that circle has a radius we'll call r. This is a good example of something that's moving in a uniform circular motion. Other examples that we're going to deal with include things like satellites, which can even include the moon. Right? The moon is an object that's moving with roughly uniform circular motion around the Earth. A ball at the end of the string, as long as you're not speeding up or slowing down that ball, that's going to be uniform circular motion. So this is one more example, along with projectile motion, which we've already looked at, of two-dimensional motion. So to begin to study circular motion, let's think about any of those previous examples we just talked about. Those are all examples of things that are moving at constant speed around a circle. Whenever something is moving at constant speed, and that's the key word for right now, constant speed, it's called uniform circular motion. Just like when something was moving at constant speed in a straight line, we called that just uniform motion. This is uniform circular motion because it's going in a circle. So when things are moving in a circle, there's some new terms that we use to describe the motion. Let's define some of those. One of those new words is called the period. So the period is the time it takes to complete one revolution. Period is a term that's going to come up over and over again. Anytime we talk about repetitive or cyclical motion of any type, we can measure the period, being the time it takes to complete one whole cycle. In this case, it's one whole revolution of the object so that it comes back to where it started from. The period is obviously related to the speed. Right? The faster an object goes, the smaller the period will be. It's going to take less time to get around. But it's also related to the radius. So the smaller the radius is, the smaller the period will be. So it's directly related to that, but it's inversely related to the speed. So let's kind of look at an example of calculating that. Imagine if we have a 4 centimeter diameter crankshaft that turns at 2400 RPM. Now what does RPM mean, first of all? Well, it means revolutions per minute. And so anytime you see RPM, that's what it's going to stand for. Let's see if we can figure out how to determine what is the speed of a point on the surface of the crankshaft. Well, the first thing we need to do, if we want to know the speed in meters per second, is we need to take that revolutions per minute and we need to convert it to revolutions per second. Because then we can use that to figure out how fast the object on the edge is moving in meters per second. So to do that, all we need to know is that there's 60 seconds in 1 minute. So we multiply 2400 revolutions per minute times 1 minute over 60 seconds, and you get that that's equal to 40 revolutions per second. So once we know how many revolutions it makes every second, we can figure out what the period is. Remember, the period is the time to make one revolution. So that's just the inverse of this number. If you know that the crankshaft turns 40 times in 1 second, then the time it takes for one revolution has to be 1/40th of a second because it has to make 40 revolutions in that 1 second. So that means that the period, which we give the symbol capital T here, is equal to 0.025 seconds. That's the time it takes to go around one time. Well, now if we know the period, we can find the speed. Remember that this average speed of something is equal to the distance that it travels divided by the time that it takes to travel that distance. Well, if an object goes all the way around a circle and it comes back to where it started from, how far did it go? Well, if we trace that path around the circle, that's equal to the circumference of the circle, which is 2 pi times r. So in one revolution, the object goes all the way around the circle once. How long does it take to make that trip? By definition, 1 period. That's what a period is, the time to make one revolution. So to find how fast it's going, we just take the distance it travels, 2 pi r, divided by the time it takes to go around, which is the period. We know the radius. In the problem, they gave us 4 centimeters diameter, so we first need to make sure we're talking about radius. need to also convert that to meters. So 4 centimeter diameter means you have a 2 centimeter radius, which is 0.02 meters. So 2 pi times 0.02 meters divided by the period of 0.025 seconds gives us a speed of 5 meters per second. Another important term in addition to period that we need to define when dealing with circular motion is something called angular position. Now, we all know what position is. That's just where the object is located in space. We've been dealing with position since the beginning of the semester. But now when we talk about things moving in a circle, it's often more important to know what angle of the circle the object is located at rather than its actual position in space. And so the angular position, again, just measures what angle it measures from usually the x-axis. And when we talk about angular position, we almost always are going to measure that angle in radians. And that's because we will use these in some calculations, some equations, and they will only work if the angle is measured in radians. So make sure that you're doing that when we're talking about angular position. If the angle is measured in radians, then there's a very simple relationship between the measurement of the angle and what we call the arc length. So the arc length is just the distance that it travels through. So we know if it goes all the way around a circle, it goes 2 pi r. But what if it's only gone through part of a circle, this angle right here? Well, then if we want to find how far the particles actually travel, if we know the radius here and we know the angle, we can multiply those together to figure out the arc length, how far the particle has actually traveled from its starting point. So r times theta. But again, theta must be in radians. Once we know angular position, then we can talk about angular displacement. So just like regular displacement for linear motion, angular displacement is the change in angular position. And so it's the final angle position minus the initial angular position. Again, with both of these measured in radians. We can also then talk about angular velocity. If you remember, velocity is equal to displacement over time. Well, angular velocity, as you might guess, is equal to angular displacement over time. We can even find a relationship for the instantaneous angular velocity. Again, if you remember, for linear velocity, velocity was equal to the derivative of the position. Well, it's really the same thing for angular velocity. Angular velocity, which is given this symbol omega right here, is equal to the derivative of the angular position. Angular velocity measures the rate at which the angular position is changing. So it measures how quickly something is rotating. The bigger the angular velocity, the more quickly it's rotating. The smaller the angular velocity, the more slowly it's rotating. We give it always the symbol of the Greek letter omega. And it can be positive or negative. Positive or negative for angular velocity is sometimes a little bit more difficult to determine than it was for linear velocity. We can tell if something's moving away from or toward the origin in that case. But here we have to look at whether it's rotating clockwise or counterclockwise. So anytime something rotates in the counterclockwise direction, that's considered to be a positive angular velocity. Anytime something's rotating in a clockwise direction, that's considered to be a negative angular velocity. Now, those relationships that we learned back weeks ago between position, velocity, acceleration, and the graphs of those things still hold true for things moving in a circle. So the angular velocity would be the slope of the angular position versus time graph, just like the linear velocity was the slope of the linear position versus time graph. The displacement is equal to the area under the velocity versus time curve, just like the linear displacement is equal to the area under the linear velocity versus time curve. So both of those relationships hold true. They're the same for linear velocity and for angular velocity. So let's look at an example problem then. If this is the angular velocity graph of a wheel, how many revolutions is the wheel going to make in the first 4 seconds? Well, to know that, we just need to find the area under the graph, right? The area tells you how much the angular position changes. You can measure the angular position in various ways. in revolutions, in radians, or so on. But in this case, we're already given it in units of revolutions per second. So all we need to do to answer this is to find the area. Well, we have two areas. All right, we have area 1 and we have area 2. So we need to find the area of each of those and add them together to get the total. What is the area of this first part? It's a triangle. So it's 1/2, 2 seconds, times 2 revolutions per second, which is 2 revolutions. All right, what about the second part here? Well, that one's a little easier, right? A2 is a square. 2 seconds times 2 revolutions per second, which is 4 revolutions. So what's the total? How many total revolutions does it make? The sum of these, 2 plus 4, or 6. Now, as we said back in the beginning, when angular velocity is constant, this is what we call uniform circular motion. In this case, as the particle goes around the circle one time, then its angular displacement will be equal to 2 pi. There's 2 pi radians in one entire circle. And so we can define then the angular velocity as it relates to the period as 2 pi divided by the period, because 2 pi is the distance that it will go in one complete revolution around the circle. Period is the time it takes to make one revolution. And these can be rearranged to solve for period or to solve for angular velocity depending on what information you actually know. Let's look at an example of this. It says as a ball rolls around a circular track with an angular velocity of 4 pi radians per second, what is the period of the motion? Well, as we just saw, period is defined as 2 pi divided by angular velocity. Now, why do we make it the absolute value? Because period is not going to be a negative number. It's a time. Whether it's rotating in a negative direction or a positive direction, it's not going to affect what the period is. It's not going backwards in time just because it's rotating backwards. So we just want to use the positive value for omega. But what was omega in this case? It says it's 4 pi. So we have 2 pi divided by 4 pi, which is equal to 1/2, or A. Let's look at another example. Going back to the roulette ball in the beginning of this lecture, imagine that you have a small steel roulette ball that rolls counterclockwise around the inside of a 30 centimeter diameter roulette wheel. The ball completes 2 revolutions in 1.2 seconds. What's the ball's angular velocity? And then let's see if we can figure out what's the ball's position at a certain amount of time after 2 seconds. We're going to assume that it starts at an angular position of 0. So what would we do? First, to figure out angular velocity, we need to know the period, right? We need to know the time for one revolution. And we can calculate that the time for one revolution is 0.6 seconds. How do we know that? Well, remember the information given in the problem. It said that it made 2 revolutions in 1.2 seconds. So how long did it take to make one revolution? Have to be 0.6. Because it's moving counterclockwise, we know that it's positive. So we know that we have a positive angular velocity. And so to calculate what that angular velocity is, we just need to divide 2 pi by the period. So 2 pi but divided by 0.6 is 10.47 radians per second. Now, how can we figure out where it is after 2 seconds? Well, we can use this equation. This is really analogous to our first kinematic equation for linear motion, right? Where the thetas represent position, angular position in this case, but it's the same equation that we used when we had linear position, and omega represents angular velocity. So now we know the angular velocity, we know the initial position, we can calculate what its final position is, 2.94 radians. Now typically, we want to know where the ball actually is in its revolution. So 2.94 radians, that's way more than one revolution. So when it asks like where's the ball located, that's technically correct. but it's a little bit hard to interpret. Like, most people don't have a good feel for when they say 2.94 radians, like, where is that? I mean, I know that I don't. So it's probably most helpful to figure out how many revolutions it's made and then where it is in its last revolution. So we can figure that out by dividing 20.94 by 2 pi, which gives us 3.333. So that means that we've completed 3 revolutions and you're a third of the way into the last revolution. And so what we can do is we can then figure out where we are into that that last revolution. It's completed 3, it's on the 4th, so it's on the 4th revolution at this point. 0.333 times 2 pi gives you 2.09 radians. We can convert that then back into degrees. So 2.09 radians is about 120 degrees. So we could say, if we were looking down at the roulette wheel, it's about 120 degrees from where it started. Finally, let's talk about how to relate angular velocity back to linear velocity. And what we call that is tangential velocity, because if we look at something moving around a circle, an object moving like this, I don't know why I made the big spike there, but we're just going to ignore that. Imagine you have something right here. At that moment, its velocity is going that way if the whole thing is rotating this way, right? When it's down here, its velocity will be going that way. When it's over here, its velocity will be going that way at that instant. So when we talk about tangential velocity, that's what we mean, the velocity that it's moving at that instant in time. It's called tangential because it's kind of just at that point that's touching the circle once of its motion. It's really easy to go back and forth between angular velocity and tangential velocity. All you have to do is multiply by the radius. Because as we said in the very beginning, both the radius also affects things like the period and therefore the angular velocity. So to find the tangential velocity, you take the angular velocity, multiply by the radius. If you wanted to find the angular velocity, you would take the tangential velocity, divide by the radius. So you can go back and forth between those. That's all we're going to talk about for today, but in a later lecture, we will come back and we will look at how to extend these ideas to situations in which you have changing angular velocity. And we're going to introduce the idea of angular acceleration.